For our next presentation, I would like to welcome Kevin Budros, an attorney with the Conservation Law Foundation of Rhode Island. Mr. Budros is in charge of the Zero Waste Project at the CLF. The Conservation Law Foundation is an advocacy organization whose mission is to protect our environment using law, science, and market. Welcome.
Thank you again for having me in. Again, my name is Kevin Budros. I'm an attorney with Conservation Law Foundation working on our Zero Waste Project. And as the title of my slide deck might give away, I have a slightly different take on this, and CLF has a slightly different take on this than the American Chemistry Council does. A brief word about Conservation Law Foundation. We are a member-supported nonprofit organization working to protect New England's environment for all people. Our Zero Waste Project is focused on our current waste crisis, trying to reorient the way our production and disposal systems work with emphasis on the zero waste hierarchy, to move towards refusing wasteful products, rethinking and redesigning our production and disposal systems so that we don't end up stuck with all of this waste after it has moved through our lives. And I'd like to just with respect to Mr. Cookson, mention a few things at the start, particularly about plastics. Mr. Cookson had a number of products up here, a number of pieces of packaging that are not conventionally recyclable. And I'd like to emphasize for the committee that the best way to move away from waste plastics isn't to try to find new creative things to do with them once they become waste. It's to just move away from them. Rather than a coffee lid, we have reusable coffee mugs. We have reusable water bottles. There are reuse systems at our fingertips right now so that we don't need to rely on plastic film and plastic packaging that we cannot recycle in a conventional way. And I'd also like to point out that producing fuels, because a lot of what we're talking about here is producing fuels from plastics through gasification. Producing fuels from plastic is not a circular economy. That's linear. You have a plastic that moves through your life, it's collected as waste, it's turned into a fuel, and fuel is burned. That is a one-way street. That's not coming back around. And I'd also like to say that plastics are not an alternative to fossil fuels. Plastics are fossil fuels. About 99% of the plastics that are produced in this country are derived from fossil fuels. Fossil fuels are the building blocks of the carbon-based polymers that plastics consist of. So, in my presentation today, I'm going to give a brief overview of gasification and pyrolysis and try to flesh out some areas that I feel need additional attention. Talk about how gasification does not generate renewable energy, it prevents waste reduction, that it has a history of failures, and that, as I mentioned before, we already have the real solutions to our waste crises right at our fingertips right now. So, brief overview. As Mr. Cookson mentioned, both gasification and pyrolysis are high heat processing of waste, be it plastic or other waste. And gasification is high heat processing that occurs in a low oxygen environment. Pyrolysis occurs in an environment entirely devoid of oxygen. And the contrast between gasification and incineration came up already. And I would agree that gasification and pyrolysis are not mass burn incineration, but they are comparable to mass burn incineration split into two parts. Mr. Cookson repeatedly emphasized that there's no combustion. But what happens to the fuel that's produced from the gasification of plastics? That fuel is combusted. So when you look at the entire process, from the actual high heat treatment of plastics or other waste, all the way through the combustion of the resulting fuels, you end up with a lot of the same emissions and a lot of the same byproducts that you end up with when you're talking about incineration. So up on this slide, I have a somewhat crowded flow chart of the gasification and pyrolysis processes, because there's a lot going on when you again account for all the different steps. And so the blue boxes and arrows on here they are inputs and throughputs in the process. The red boxes are kind of the key steps in the overall gasification process. And the yellow arrows are outputs, emissions and solid waste. So when you take dry waste, be it plastics or municipal solid waste, because if we're talking about exempting gasifiers from solid waste regs, we need to understand that we could run into a situation where we're not just talking about gasification of plastics, but gasification of mixed waste. When you feed waste into a high heat chamber, you get the type of hydrocarbons that Mr. Cookson was talking about. But again, you also generate slag, char, dust, ash, other solid waste products. And in further slides, I'm going to go into detail on what are the toxics that are in those solid waste outputs. You end up with those liquid hydrocarbons, but particularly if they're going to be used as a synthetic fuel, they need to be filtered because there are a lot of contaminants in those fuels when they come out of the high heat chamber. And those contaminants are filtered out. They include nitrogen oxides, sulfur dioxides, heavy metals like lead and mercury, POPs like dioxins and furans. Sorry, POPs are persistent organic pollutants like dioxins and furans, all acutely toxic materials. And then, as I mentioned before, that synfuel is eventually combusted, whether it's combusted on site at a gasifier or if it's shipped off and used in vehicles or in an energy generation facility. And because you don't clean out all of the contaminants in that fuel, you end up again generating nitrogen oxides, sulfur dioxides, metals, POPs. And so breaking it down a bit further, those solids that you end up with from the heat chamber, the slag, the ash, the char. Mr. Cookson mentioned that it's pigments that are associated with the plastics and other relatively innocuous things. That's really not the case. If you're treating plastics with high heat, you end up with dioxins. Dioxins are often referred to as the most toxic chemicals known to humankind. They're known carcinogens. They can result in neurologic damage, developmental toxicity, kidney and liver disease. This is really toxic stuff that we're talking about. And it, along with mercury and lead, end up in this solid waste product. And you have to figure out what to do with that waste product. It can either be landfilled, which exposes communities near landfills to the risk of exposure to these toxics, or you can incinerate it, which just emits a lot of these toxics into the air. You then end up with that fuel mixture, which, as I mentioned before, needs to be filtered out. And those contaminants that you filter out, again, include nitrogen oxides and sulfur dioxides, which are lung irritants. They contribute to smog and other detrimental environmental effects. You again end up with heavy metals like mercury and lead, which have significant impacts on human health. And those dioxins, furans, PCBs show up again. And then you get your synthetic fuel, which still contains many of those contaminants, and which is then combusted, again, either on site or at a different facility or in a vehicle. And the air emissions include carbon monoxide and greenhouse gases like carbon dioxide. And we see a lot of the same offenders coming out of the combustion process here. Nitrogen oxides, sulfur dioxides, heavy metals, persistent organic pollutants, and also particulate matter. When you look at the synthetic fuels that are generated from gasification of waste, be it plastic or mixed waste, the emissions profile is actually worse than the emissions profiles of fracked gas, diesel, and gasoline. So we're talking about a actually quite dirty fuel that's generated from this process. And up here on this slide, I have a head-to-head comparison between gasification and mass burn incineration. When again, you account for all of these steps in the process, not just the conversion to synthetic fuel, but the cleaning of that fuel and the combustion of that fuel. You end up with the same byproducts and emissions and solid waste. You get your heat, but you also get your ash and your char, your carbon dioxide, nitrogen oxides, sulfur oxides, heavy metals, and persistent organic pollutants. And so that's kind of the soup to nuts profile of what you kind of get out incidentally of the gasification process. But it's also important to note that Gasification doesn't generate renewable energy. This isn't that circular process, because if you're converting materials that contain stored carbon, you're releasing that carbon to the atmosphere when you burn the synthetic fuel. And as I mentioned earlier, plastics, 99% of plastics are fossil fuels. If you're turning plastics into a fuel and then you're burning that fossil fuel, it is the equivalent of burning a fossil fuel. You just took a fossil fuel, gave it a brief lifespan as a plastic, turned it back into a fossil fuel and burned it. That's not renewable energy. That's linear. And especially if you compare high heat technologies like gasification or pyrolysis to zero waste alternatives like source reduction, recycling, composting. Those processes conserve far more energy than you could ever hope to generate out of a gasifier. So by moving to waste reduction processes, we can save more than we could hope to make off of the gasifier in terms of energy production. And importantly, gasifiers waste energy. I know Mr. Cookson said that you generally need just a small amount of natural gas to run these pyrolysis reactions. But in a gasification or pyrolysis chamber, and the technologies differ widely from facility to facility, you're talking about temperatures from 700 degrees Fahrenheit to 2,800 degrees Fahrenheit. Those are intensely high temperatures. You need a lot of energy to generate that type of reaction. And so these facilities consume as much as 87 times more energy than you can hope to get out of the facility in the form of a synthetic fuel at the end of the day. And that's because the laws of thermodynamics are inviolable. If you need to generate so much heat to create a fuel, you cannot get more energy out of that fuel than you used to create the fuel in the first place. That simply doesn't work. And in part because of that high energy consumption, but in part because of high capital costs for gasification facilities. Gasification is really quite expensive. If you view it through the lens of energy generation, industry estimates on a kilowatt-based generation capacity suggests that it costs between $7,500 and more than $11,000 per kilowatt capacity to build a gasifier or pyrolyzer. So a gasifier with a 15 megawatt output is going to cost as much as $172 million. And that's more than twice the capital costs on a kilowatt hour basis than wind and solar energy. And high costs mean high tip fees. If these facilities are expensive to build and if they're expensive to run, it means that they're going to have to recover money by charging for the waste that they're collecting, be it plastic or mixed waste. And I know that we've been talking mostly about gasifying plastic so far, but again, if we're exempting gasifiers from the solid waste regs, we run the risk of gasifiers that are burning mixed municipal solid waste. And gasification and pyrolysis are intended to burn homogeneous fuel sources. Municipal solid waste is anything but homogeneous. That up there in that pie chart is the breakdown on what's in our waste in the state of Rhode Island. So it's spread across paper, plastic, glass, metal, organic waste, construction and demolition debris. It is very difficult to maintain the ideal reaction conditions for a gasifier when you have a mixed type of waste. And importantly, gasification gets in the way of the real solutions here, which are waste reductions. Because gasification and pyrolysis facilities rely on carbon-rich feedstock, like that plastic, and like organic waste, and like paper. And so they're competing with preferred strategies like source reduction. Again, if we want to get rid of the plastic film in our life, let's get rid of the plastic film in our life instead of trying to convert it to fuel after its short lifespan. And they compete with recycling and composting and anaerobic digestion when we're talking about organic waste. You can't feed the beast and reduce waste at the same time. When you build one of these facilities, they need feedstock all the time if they're going to be financially viable or if they're even going to approach financial viability. And I have up here again a comparison of gasification and zero waste alternatives. And high heat treatments like incineration or like gasification are significantly more expensive than alternatives like composting and like recycling. And not only are they more expensive, but at the same time, they also generate fewer jobs. Composting can generate between 4 and 15 times as many jobs as gasification. Recycling can generate between 12 and 20 times as many jobs as gasification can. And because of all of those challenges, gasification has a long history of failure. I know that Mr. Cookson brought up some examples in the US, and most of those are recent examples because the attempts to bring gasification to the US are relatively new. But other countries have 2 decades course of gasification failures. So up here on this slide, there is a facility in Scotland called Combustion that was built, consistently exceeded its emission limits for acute toxics like dioxins, generated less energy than was expected, and its operating permit was eventually revoked. Same thing for the Plasco facility in Ottawa, which closed in 2015. It failed to comply with its emission limits, again on dangerous pollutants like sulfur dioxide. It only processed 7% of the waste it was contracted to process, and its parent company ultimately filed for bankruptcy. Another facility in Scotland, not only did it fail in 2009, but the public council that invested significant sums of money in that gasifier lost £11.5 million on the failed project. A facility in Germany, again, violated emissions limits for pollutants like dioxins, struggled, and its facility owner lost the equivalent of $500 million. And my last example in Australia, a facility that again had significant emissions limits violations and lost the equivalent of $134 million. So again, we have the solutions to our waste problem right here at our fingertips. We can cut the plastics out of our lives through things like plastic bag bans and restrictions on plastic film and polystyrene food container bans. We can move to source reduction through measures like extended producer responsibility for packaging, which puts the cost of all of this waste on the people that are making it rather than on our municipal and state governments. We can improve our recycling systems, and importantly, we can pivot to much wider scale composting and anaerobic digestion, and we can divert that almost 1/3 of our waste that's organic waste right off the top. So Rhode Island can reduce its emissions, it can save money, and can protect its communities by pivoting to these zero waste alternatives. Gasification and pyrolysis should not have a future in Rhode Island because they're incompatible with a healthy, thriving state. Thank you.
Kevin, thank you very much for your presentation. After listening to you, I wish I had spent more time in chemistry in school.